Greetings, isolated machine component designers. Today we're going to talk about um, bolt fatigue, and it's kind of a funny topic because you're getting sick of doing bolt problems, and so bolt fatigue has a kind of a double entendre. But let's see, what are we going to do here? So this is really just kind of a rehash of section 10.11. In the book. Now, 10.11 could be almost a whole chapter, in my opinion. So I'm going to expand on just this one section in my own words. Basically, the setup is that we're going to bolt a joint with an M10 by 1.5. Right? What does this mean? It's metric, 10 millimeters, and the thread pitch is 1.5 millimeters. Grade 8.8. Bolt, right? This just tells us something about the material. And then we're going to put an external load on this thing, right? And this external load will fluctuate, hence fatigue, from 0 kilonewtons to 9 kilonewtons. And the kind of important thing about this is we're going to pre-tension this in a couple different ways. One way we're going to do it, let's turn the pen on here. One way we're going to do it, we're going to just do it by feel, and I'll show you what I mean. And then the other way we're going to do it will be to pre-tension this correctly. Okay, so I'm going to try some audio-visual trickery here. It just so happens, surprise, surprise, that in my shed I have an M10 bolt. As you can see, this is not, those three little hash marks there, mean that this is not in fact, wow, that's really not working well. This is not in fact a grade 8. This is actually a grade 5 bolt with the three little hashtags. But I don't have any expensive bolts. I just have the cheap stuff. And this is in fact an M10. And it's got 1.5 millimeters between the threads. And so that's what we're going to work with today. And then pre-tension by feel versus correctly. All right, let's see. And then really what I'm interested in is just to investigate the stresses. Right, and that's pretty much what the whole class is about, is investigating stresses in these components. All right. So the first thing we're going to do is tighten this thing by feel. Now, I would say we all, most of us probably have gone to the hardware store, and we're working on a project, we're fixing something, building something, senior design project, whatever. And so we say, oh yeah, that looks like about the right size bolt. Right? So you get the bolt, you get a couple washers, you put the nut on it, and then you say, okay, this is good. Right? So you do this totally by feel. You just based on what looks right. Now remember, as I tighten this thing down, if I put my fingers between here and I crank this down, I'm squeezing my fingers between the two washers. Meanwhile, my fingers are in fact stretching the bolt just a little bit. If we were to really crank on this, my fingers would lose for sure. Now, what do we all do? We get our handy 16 millimeter wrench, because the 16 millimeter wrench does in fact match the 16 millimeter nut that goes with this bolt, and then we put it on here, right? Oops, that's the wrong one. Let me get the right wrench here, guys. I know why. Okay, so whatever. So we put the 16 millimeter up here, and I crank on this, and what happens? Right, it gets tighter and tighter and tighter. How do most people tighten these things? They put their hand on it, they tighten, they pull pretty hard, and they call it good. So what would be pretty hard? Let's say the moment arm here is about 6 inches, and I can pull on this with, let's say, I'm an old man, maybe not as strong as I used to be, 30 pounds. How much torque am I going to get? Okay, so I'm going to use a wrench to tighten this thing, which is approximately 6 inches long, which is 0.5 feet. To my wrench, I'm going to apply some force from my hand, which we estimated is going to be 30 pounds. Right, so that means my torque is going to be 15 foot-pounds, and in much better SI units, that's pretty close to 20 Newton meters. I know from previous work that the torque required to achieve a certain initial tension works out to be 0.2 times the initial force that I'm after, times the diameter of the bolt. Now it's very important, so this is an estimate because I don't know what my friction is. Rusty, not rusty, new, old, lubricated, not, we don't know. But anyway, we can use this and say that my initial force will be, how does that work out? Torque divided by 0.2d. Let's see, the torque, we decided is 20 Newton meters, and I'm going to divide that by 0.2. What should the diameter be? Well, I want to get newtons, so that means I want to do this in meters, which means it's 0.01 10 millimeters. So that means my initial force is going to be 10,000 newtons. Wow, that's amazing. So just with my wrench, I can get 10,000 pounds of tension on this thing. So I'd say that's a pretty important intermediate step. All right. Now, when we take a look at the bolt tension and the clamping force, all right, so I'm going to take a little bit of time to explain this. My initial force due to torque was 10 kilonewtons, right, which means initially that my pretension force is, of course, equal to the force in the bolt, which is, of course, equal to the clamping force, which is all 10 kilonewtons, right? And now, due to geometry, I'm going to say that the stiffness, right, as far as the spring stiffness of the clamped plates, is about 2 times the spring stiffness of the bolts, right? Why is that? A lot of people struggle with this. So here's 2 plates that got clamped together. Here's the other side. We have some bolt going through there, like that. So this has some area in here, right? But when I clamp it, it kind of makes this cone-shaped thing here that looks like that. And I'm going to say that this has 2 times the area. So because of the greater area, the plates are stiffer than the bolt. All right. Well, let's draw this somewhat confusing picture. A lot of people struggle with this, so let's spend a little bit of time explaining this. This is the applied external force, and this axis up here is, I'm just going to call that force, right? Well, what is this force here? It's the force in the bolt and the force in the clamped members, all right? So this is tension, and this is compression, right? And at first, those two are equal, right? We've got 10 kilonewtons is our initial tension. But as I apply 9 kilonewtons of external force, right, what happens? The bolt is stretchier, so as it increases in length, as this external force acts upon it, right, it only picks up how much of it is that, so the fraction that the bolt carries, fraction carried by the bolt is the stiffness of the bolt over the total stiffness, right? But I know what the clamped members are, and that is 2 times the bolt. So this equals 1/3. So when I apply this 9 kilonewtons, this section here is only 3. Well, what happens to the other 6? It must get picked up by a reduction in the clamping force. Right? And then necessarily, the total change in force is the total external force that I applied. So this is the full 9 kilonewtons, right? Okay, so now we've got a little bit more tension in the bolt and a little less compression in the plates. But this is a fatigue problem, so we need to look at we need to look at the mean and alternating stresses. First things, it's fatigue. Right, what does that mean? That means that the stress concentration matters. And so we'll look in table 10.6, and we'll discover that I think I used rolled threads for this. The stress concentration is 3. Okay, so initially, my stress is the initial force over the area, and that'll get multiplied by the fatigue stress concentration factor. This is 10,000 newtons divided by what area do I use? I've got to go back here. And the area that really matters here is the stress area, right? I've got all these different areas. I've got a minimum area, but this is the one I'm after here. So this is my 10 millimeter bolt, and the effective stress area is this 58 millimeters squared here. So I've got to use that. 58 millimeters squared. That's nice because a Newton per millimeter squared is a megapascal. So this works out to be 517 megapascals. All right. Now I'm going to add 3 kilonewtons. Right? Why 3 kilonewtons? Because that's the bolt's share of 9 kilonewtons. And that will result in sigma, well, let's call this a sigma initial, sigma load equals 13,000 divided by the same area. Times 3. So that results in 672 megapascals. But we have to pay attention to something here. That if I look at the yield stress of grade 8.8, so I'm looking down here. If I look at the grade 8.8, the yield strength is only 660, right? So what's going to happen there? Where are we here? So since it's 660, we've exceeded that yield stress. So there will be a little bit of yielding. What does that look like? It looks like this. So here's a zoomed in section of our bolt. Looks something like this. Right here at the red dot. So that's our concentrated stress. Right. Everywhere else, it doesn't really apply. Right. So this down here is Well, the red is the 672. And then everywhere else, the stress turns out to be quite a bit less. So the mean stress is 224 megapascals. And the concentrated stress is in megapascals. So as a result of that, and you've done this in 307, I know, it was too much work. We can kind of plot this stress, and it looks like this. High at the corners, high at the stress concentrations, and then relatively low in the middle. So it will yield such that, this stuff will yield here, right? And it offloads, there's some of this load sharing that happens, so some of the load gets picked up by the neighboring fibers of metal. So it'll all drop down to 660. So it's at 660. Let's write that down. This drops to 660 megapascals, and there'll be some load sharing. All right. Well, what happens when I release the load now? And so stress drops by 3 kilonewtons divided by 58 millimeters squared times 3 equals 155 megapascals, right? So the stress will alternate between sigma max will be the yield stress, right? Because it won't get any higher than that. And then sigma min will be, well, it drops by 155, so that's 505 megapascals. Where did I get that 505? That's 660 minus 155, okay? So mean and alternating stresses then, let's see, sigma mean, what does that work out to be? It's this plus this divided by 2, so 583. And then the sigma alternating is half of the difference, so the difference is 155, so that means the alternating stress is 77 megapascals. All right, and those are pretty important, so they're going to get a dotted box. All right, what do we do next? Anytime we do a fatigue problem, we need to draw ourselves a Goodman diagram, so let's do that. On the Goodman diagram, we have sigma mean and we have sigma alternating. We have an ultimate tensile strength, which for this, what is it for this? Let's go back and check that out from the table. The ultimate tensile strength down here, 830. Okay, that's good to know. So we'll put that on our Goodman diagram. 830. And then up here, what do we need? The endurance strength. So S sub n. We don't know that. It turns out for bolts, it's the same, 0.5 times SUT. But then we have to multiply that by 0.9. Why is that? Because this is an axial load. Remember, axial load is bad for fatigue stuff. And then surface factor, 1.0 for surface. And since this is relatively small, 1.0 for the size factor, or the gradient. And so for grade 8.8 stuff, we'll have a fully corrected yield strength, or a fatigue strength of 373 megapascals. So that's 373. And then we draw a line, from there to there. Now, we should also worry about yielding, right? And the yield stress, what was that? I'm going to use my photographic memory and remember that SY equals 660 megapascals. And so the 660 is up there. So we draw this roughly 45-degree line that goes like that. Okay. And then now what were our mean and alternating stresses? Let's see, 583 and 77. 583 and 77, it works out to be right about there. So that is, 583 and 77. So here's 77, and here is 583. Okay, so that's where we're operating on this Goodman diagram. So we're well within, this is infinite life. But as we saw, we do yield slightly. But it's not really a big deal because it yields totally axially. Yields axially. Still works. All right. So that's a Goodman diagram. All right. So before we had 10 kilonewtons, which we were pretty proud of ourselves for using a 10 kilonewton force, and just with our bare hands. But this time we're going to pretension to the full yield stress, right? Not realistic, but easier to calculate. So we'll make in blue. Typically, let's zoom in on this a little bit. Oop. Uh-oh, that's not what I meant to do. So typically, pretension to approximately 90% of proof. But things will be a little bit easier if we go to the full yield stress here. All right, so what happens with this? The initial force, right, we want to take it all the way up to yield, so we're going to take it to the yield strength and the effective tension area. So that works out to be, what was the yield again? 660 megapascals times 58 millimeters squared. So we get an initial tension of, what do we get? 38,280 newtons. Wow. So the yield strength of this bolt, right, that I'm holding in my hand is 38,000 newtons. So roughly 9,000 pounds. Let's put that in. Right, so I could hang my minivan by that bolt, right? And we thought 10,000 newtons, we're doing something, not really, right? So the full yield load on this bolt, before we add any load, the force initial is the same as the force in the bolt, which is the same as the clamping force, and that's 38 kilonewtons, all right? Now let's apply a little bit of load. All right, we'll apply some external load. So again, here's our external load. Here's our force. And we're going to start at a relatively high 38 kilonewtons. Right, and then we're going to apply this 9 kilonewton external load. So what happens? What are the stiffnesses? K. The KB equals 2 times KC equals 2 times the KB, right? That's twice as stiff, but not right now. No. Why is that? Because at 38,000 pounds, bolt starts yielding, right? So it's just going to stretch. It's got no more fight left in it. So I'm going to go like this. So it yields with no additional stress, right? Which means to keep this thing, so if this only has 38 and I've got a 9 kilonewton external load, right, this is going to drop by 9. FC drops by entire 9 kilonewtons. So this goes down to here. So we drop down, this is still 38 because it doesn't pick up any extra load. And so this drops down to 29 kilonewtons. All right. So that's a little different than what we're used to. And even with the load applied, even at full external load, sigma, let's try that again, sigma in the bolt is still only 660 megapascals. Okay, now we're going to do a quick flashback to ME307, right? It's too much work. So we'll draw this, and we're going to make ourselves the old stress strain curve here. So what happens? I've got this perfectly elastic strain, and then ideally, as soon as I hit the yield stress, this thing just levels out like this, right? And then of course I've got the Young's modulus here. We call this, this is the perfectly elastic. And this is perfectly plastic. So when I load this thing up, when I apply this this large external load, what's going to happen here? I'm going to go up, 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 up. But I continue to load it, and so the clamped members then take up all the rest of it. The bolt doesn't get any more. So this is so this point is kind of like the pretension, or F sub I, right? And then I'm going to continue to stress it. So this is after I apply the external load. It goes like that. So this results in some elastic strain. And then I just plastically stretched my bolt, and I got some plastic strain. But now, what happens when I release the external load? Right, when I release that external load, I get this. Right, it still slides back by this much here, right? And because I get the elastic stuff back, the plastic, so this is the permanent, what we call, this, I'm running out of colors here. So this dimension here is called the permanent set, right? So I actually stretched my bolt a little bit, but I did get some elastic back. How much elastic back did I get? Well, I will get back, so elastic deformation relaxes, and so the stress becomes stress reduces by 3 1,000 newtons over the full 58 millimeters squared equals 155 megapascals, right? So that means after I release this, how should I draw that? No. So the force in the bolt now, so FB was initially, what was it, 38 kilonewtons? After first load, it stayed at 38 kilonewtons because it yielded. And then after release, drops to 35 kilonewtons. So what does this mean? My effective preload becomes 35 kilonewtons. Right? I yielded it, released it, and then I'm left with 35 kilonewtons on this thing. Right? Okay, so it drops by 155, so I have a sigma max. Right, I took this all the way up to yielding, so that was 660 megapascals. I released it, it dropped by 155, so sigma min equals, let's see, 660,505, which means my sigma, these numbers look familiar, my mean stress is 583. And my alternating stress is 77 megapascals. Well, those look familiar. Right? I would say let's draw another Goodman diagram, but no, we don't need to draw another Goodman diagram because this Goodman diagram still applies, right? So this point does not rely on my initial tension. Wow, that's amazing, right? So what does that allow me to do? I can tighten this part way, or I can tighten it all the way up to its full yield stress, and the fatigue characteristics, the fatigue implications remain exactly the same. All right, so why does this matter? Okay, let's draw another one of these force diagrams. We'll start over here. And we'll go all the way over here. Remember, this is my force external. This is my force. So I've got two options. One, basically I loaded this thing to 38 kilonewtons, but then it'll yield when I added the extra. So I pre-tensioned to 38, loaded another 3 kilonewtons, and then it stretched back to 35. So and this is after, I'm going to put that in blue, after first load and release. And then my other option was to just put a measly 10 kilonewtons on it. Right? Both cases, I'm going to add 9 kilonewton external load. So this thing is not exactly to scale, but close. At the 10 kilonewton preload, I know that this takes up 1/3 of it, so this goes up to 13 kilonewtons, and my clamping force goes down to, well, let's see, that took 3, so that must be 6, so that goes down to 4 kilonewtons, like that, right? Alternatively, this will go from 35, it can go all the way up to 38, because that's where it yields. and then so it goes up by 3, and the clamping force then reduces to, let's see, up by 3, down by 6, so 29 kilonewtons. Right? Well, why do I care which one of these works? Right? Big pretension. I could give it a really big pretension, and then I get some alternating force on the bolt that looks like this. Or I could give it some small pretension and get some alternating force on the bolt that looks like that. What's the difference? Right? Well, why do I even bother? So I'm going to ask a little question here. What happens in an overload? I.e., I've got greater than my 9 kilonewtons. Well, if that happens, in the high pretension case, right, my clamping force, so I still have clamping force, so it doesn't leak or it doesn't separate or whatever. And actually what happens here, the bolt yields a little bit more. So that happens there. The bolt yields slightly. So no big deal. However, what happens here is the clamping force goes to 0. And then the bolt force continues to go up. But what happens here, as soon as the clamping force goes to 0, the plates have separated. So now all the external load, so all additional Fe goes on the bolt, right? So that's bad. As soon as my clamping force goes to 0, all the external load goes on the bolt, and then we're in danger of exceeding the ultimate stress, in which case this thing breaks. Okay, so it's counterintuitive that by providing a much greater initial tension up here, we're actually protecting the bolt from failing. Whereas a low pretension means that we're in danger of putting all the load on the bolt and possibly exceeding the ultimate tensile strength. It's counterintuitive, but hopefully this will help you guys with your upcoming homework. Take care.